So what we're going to look at is an observation that we can make, or a couple observations really, because of division. And we're going to look at first is what's called the factor theorem. And it works like this. Let's say we take p of x and we divide by x minus c. So we do our usual setup. X minus c and the p of x. And we do our calculations. And then at the very end, we find out we have an answer q of x, and there's a remainder r. So when we write our answer, we say p of x is, we take p of x, we can say it's divided by x minus c. And when we do this, we get an answer of q of x plus r over x minus c. So we perform the division, we get q of x, which is what we got. And then we have our remainder, we add that. But remember, we always divide the remainder by this divisor. And so that's our answer. Now, the opposite of multiplication is, or division is multiplication. So let's multiply both sides by x minus c. These two will cancel each other out. And then we're going to multiply everything here by x minus c. So this will cancel. We get p of x is equal to x minus c times q of x plus r over x minus c. So we're distributing x minus c here, and so what we get, p of x is x minus c times q of x plus x minus c times r over x minus c. X minus c's cancel, at least here they do. And so what we're left with is this. P of x is x minus c times q of x plus r. So all right, we can write p of x in terms of what we divided it by and the answer that we got, including the remainder. So it's a way of sort of breaking p of x down. So what the factor theorem notes is this. If we take p of c, we replace x with c, we're going to get this. This is 0. So P of C is equal to R. Well, all right. Interesting. So if we divide by x minus c, and then we go back to our polynomial and we put c in for x, we get the remainder. So what happens if P of C is equal to 0? Well, if P of C equals 0, this means R must equal 0. And so what that's going to imply is that P of C equals 0 means x minus c is a factor of P of x. In other words, since r is 0, we can rewrite this like so. So if there's no remainder here, this is a factor of P of x. So this is the factor theorem that essentially if P of C equals 0, then x minus c is a factor of P of x. Or in other words, we can rewrite P of x as x minus c times some other polynomial q of x. And we don't have a plus remainder term here. And another way you can think of this, if x minus c is a factor of P of x, then P of C is equal to 0. So if you have a polynomial and you say, try a number, guess a number, say 4. Let's put 4 into our polynomial, let x be 4. And if it comes out equal to 0, that means we can write this in terms of x minus 4 times, well, some polynomial. That's going to be equal to P of x. And this is going to be useful later. This is where the power of this idea comes from. Let's say we have some idea of some number c that makes our polynomial equal to 0. Well, then we know we can rewrite our polynomial like this. That means to find this, we're going to divide by x minus c. And when we get to the rational zeros theorem, this is actually what we're going to do in the next section. We're going to actually come up with a way to properly, or not properly, but with some success, hopefully, guess a c. Because right now we can just, okay, here's a polynomial. Let me try 5, see what happens. Well, when we get to the rational zeros theorem, we're going to have some guidelines on how to guess a c that'll work. And that means we can rewrite our polynomial. If the c does in fact work, we'll have to test it. But if it works, if p of the c that we, use our guidelines to guess, this equals 0, we can rewrite the polynomial like this. And then we can find this by dividing P of x by x minus c using synthetic division. Then we can look at factoring Q of x, and this will help us factor the polynomial. All right. So that's the factor theorem. Now, there's an application to this called the remainder theorem. And so the remainder theorem works like this. Let's say we have P of x is x minus c Q of x plus R over X minus C. All right. So, oh, sorry. We've got it like that. So we have our P of X like this. If we divide it, if divided by X minus C, we'll have this. So when we perform the division, we get this. But what we saw earlier is we can rewrite P of X in terms of what we divided by, the divisor, the answer we got, and the remainder. So given this, we made the observation earlier that P of C is C minus C, Q of C plus R. And this will become 0 because this is 0. So we get P of C is equal to R. So here's the idea. If P of X divided by X minus C has a remainder R, then P of C is equal to R. That's it. So if we divide this by X minus C, we're going to get some remainder R. Well, we can come up with this remainder R by computing P of C. So there's another way you can think about this. Let's say we want to figure out what P of C is. And the application of this, let's say we have some really gnarly polynomial. Say it's like X, like let's say it's a 23rd degree polynomial. And you want to figure out, it's got like all the terms too. All of them are there. There's the degree 24, the degree 23, the degree 22, all the way to degree 10, degree 9, degree 8. And you want to figure out what's P of 3. You know, what happens if you replace X with 3? Well, that's a lot of computations. It's going to get pretty gnarly doing all those powers. So maybe doing synthetic division, dividing this by polynomial, instead of by substituting X with 3, divide the polynomial by X minus 3, and maybe, hopefully, the synthetic division, those calculations aren't as complicated. And that the remainder we get at the end, well, that's what P of 3 would be. So let's look at an example. Let's say we have this. And let's say we want to find P of 4. Well, we could substitute 4. And we got to come up with 4 cubed times 2, 4 squared times 11, 7 times 4, and then add and subtract accordingly. But maybe this could be easier with synthetic division. So in synthetic division, we're taking this in this case, we'll do X minus C. So if this was a negative number, we would have X plus 4, because X minus a negative 4 would be a plus 4. But since it's a positive 4, we do X minus C, so it's X minus 4. And then we set this up, instead of doing polynomial division, or long division, which is what we've been looking at earlier. And then we realized we could use this synthetic division, where we rewrite this like so. And again, since it's a minus, it becomes a plus. If this was a plus, you would have a minus. And then we keep the coefficients in constant term. Don't change signs on those. And bring down the lead coefficient. And then we do our multiplication. 4 times 2 is 8. And we're always adding in this case. While with long division, we're going to be subtracting. Synthetic division, we add. So you have minus 3. And then 4 times minus 3 is negative 12. Add. Minus 5. 4 times minus 5 is minus 20. We add those, you get minus 25. So if we divide this by this, and then we use synthetic division to make it a little easier, this is our remainder term. That would be the constant term. That's the coefficient for x. And that's the coefficient for x squared. Now, according to the remainder theorem, if we want to find p of 4, we just have to divide this polynomial by x minus 4. And whatever remainder we get, that's actually what p of 4 is. So if you take p of 4, divide by x minus 4, the remainder is p of 4. So what's the remainder? Negative 25. And so that's the answer. P of 4 is negative 25. So the idea here is that maybe doing these calculations is easier than putting 4 into x and then doing the multiplications and the additions and subtractions, especially when you get high power things like that, or larger exponents, larger than, say, 3. So that's the idea of the remainder theorem. If you have any questions about that, let me know. Otherwise, have a wonderful morning.